Good morning, Witsies. My name is Dr. Jacques du Plessis. I work at the Wits School of Education, and I am going to try and teach you some very, very important mathematics that you need to do well in certain sections of calculus. Our first video is going to be looking at how rational numbers behave if we change the denominator in different ways. And just to remind you what a rational number is a fraction. It's anything that can be written in the form a over b, where a is an integer and b is an integer. Okay, so we do not have things like 1 over root 2 being a rational number. That cannot be the case. Okay, let's have a look. If I start off and let's choose a number, let's say 3 over 2. Okay, we all know that 3 over 2, if you put it into your calculator, you'll see it's 1.5. Okay, and what is 1.5 as a decimal number? That is 1,5. Okay, so if we work at 3 over 2, we have 1.5. Now we're going to take our denominator and we're going to increase the denominator with a factor of 10. So if we look at 3 over 20, by increasing with a factor of 10, we are timesing with 1 over 10. So if I make this 10 times bigger, you'll see if you plug it into your calculator, this becomes 0.15. So the denominator is increased with 10, and this has decreased by a factor of 10. Now let's increase our denominator with another factor of 10, so that becomes 3 over 200. Then punch it into your calculator, you'll see it becomes 0.015. So it's even smaller than the previous number. So let's just see what we're doing. We're making our denominator bigger, and the actual value of our numbers becoming smaller and smaller. If we increase it by another factor of 10, in other words, we 3 over 2,000, this number decreases by a factor of 10. So there we go. We have 0.0015. That is very small. That's getting closer and closer to 0. Let's jump a few and let's go to 3 over 200,000. Now punch it into your calculator and you'll see you get 0.00015. Now that is pretty small in my book. That's getting closer and closer to 0 as we increase our denominator with factors of 10. So if we need to summarize what we saw, what just happened, I took 3 and I'm going to write my denominator as an n in this case. And let's talk about that. As that n became bigger, so in other words, it's approaching a very big number. Now, let's just talk about what infinity means. Infinity means the number is incredibly large. It's a very, very big positive number. And you can see, we started at 2, and just 5 later we were at 200,000. So infinity is large. It is very huge. You can think of it as a 2 with, let's say, 25 million zeros next to it. Okay, the point is, the denominator is becoming bigger. As the denominator becomes bigger, the value of the fraction we saw is approaching 0. So if we change our denominator and we make the denominator bigger, the value of our fraction approached 0. Listen carefully to the language that I'm using. Okay, let's now go and see what the opposite process will be. If we start with 3 divided by, in other words, we start with, let's first look at what we had there, and let's now reduce this to 0.2. So in other words, we took the 2 at the bottom and we divided it by 10. So it's no longer on the right-hand side of of the 2, it's going to the left. It's getting smaller and smaller. Now, if I punch that into my calculator, immediately, instead of 1.5, I have 15. And let's continue the process. 0.02 in the denominator would mean that this number gets bigger by a factor of 10, where at the top they became smaller as the denominator became bigger. Now our denominators are becoming smaller by the factor of 10, and the value of the number is increasing by a factor of 10. So if we continue, 0.002, and you're very welcome to use your calculator, folks, to check whether this is indeed the case. So we've reduced that, and this is becoming larger and larger. One more, 0.0002 would mean on the right-hand side, if I type in this in my computer, on my calculator rather, I will have a value of 15,000. So as my denominator is decreasing, I can see that the value of my function, of my number over here, is indeed increasing. So let's summarize that. I'm still with the number 3 over n, but this time I looked at as the denominator of this rational number approaches 0. So it's becoming smaller and smaller and smaller. It's getting closer to 0. The value of this fraction is increasing. And eventually, if we have 20 million zeros after this decimal and then a 2, we will have a number that's too large to determine. So we are approaching infinity again in the same way as what we did before. Okay, so I hope that helped you to understand how the rational number behaves when we look at our numerator and at our denominator moving into either a bigger number or into a smaller number. What happens to the fraction? Let's go back to something that you're quite used to from school. And that is the idea of the hyperbola that you worked with at school level. What I've got sketched for us on this diagram is the graph of y is equal to 1 over x. But I don't want us to think about it as that. I want us to think about it as something different. So let us take this x and multiply it across, and then see what the hyperbola is actually made of. If I times both sides with x, it is saying to me that what's represented on this graph is the product of two values, and that product gives me 1. Now let's see if that's the case. Let's just look at this point over there. That's the point where x is 1 and y is 1, and the product of 1 and 1 is indeed 1. If I look at the point that lies over there, the y value is 2, but if I come down here, the x value lies at a half. And yes, a half times 2 is indeed 1. So every point that's represented on this red function is a product of x and y, and it leaves me with a value of 1. Now let's just go back to the original function. We have 1 over x. Now 1 over x is problematic for one reason. There's a denominator with a variable in it. So we know, and we must remind ourselves, that that x cannot be naught. Now if we look at it in that language, the language of the rational number, it makes perfect sense. Let's go and see how do we approach the same thing as a product. For a product of two numbers to not be 0, folks, I'm saying it slowly, a product of two values, two numbers, to not be 0, in other words, in this case 1, none of these two numbers, x cannot be naught, because if x is naught and I times it with y, I get naught. I don't get the constant on the right. And for the same argument, y can also not be 0. Okay, so let's see, how does this feed into the idea that we just started talking about? As the x values become bigger, what happens to the y values? Well, let's see on the graph. X is becoming bigger and bigger and bigger and bigger as we move to the right. The y values are coming down, and they in fact are becoming smaller and smaller and smaller and smaller. And if I had the ability to go up to 8 million here, you would see that it lies very close to my x-axis, which lies over there, and then my y-axis there. So it gets closer and closer to the x-axis, but it never crosses it. The same goes on to the negative side. As I move to the negatives, the numbers, please folks, remember, are not becoming bigger. If I move on the system of axis, if I move to the right, the number becomes bigger. If I move to the left, the numbers are becoming smaller. But there's a negative in front of them. Okay, so they're to the left of the 0. So we can think of them now. It's a very good idea, and I want you to understand this very, very clearly, folks. That even though I am moving to the left of 0, the numbers are becoming smaller and smaller. But when I plug them into the rational number, I can think of them theoretically as a very big negative number, even though they are very small. So the -8, when I plug it under here in my rational version, this becomes -8, will have the same value as what it will have when I put a positive 8 in, except for it will be the additive inverse of the positive 8. So it will only have an additional negative with it. Okay, so in here, as my x is approaching infinity, it's becoming bigger and bigger, my y values are approaching 0. And now remember, what is my y value? My y value here is 1 over x. So in fact, I'm saying 1 over x is approaching 0. And the same goes for this side. As x is approaching a very small negative, in fact, but I'm thinking of it as a big number. If I ignore the negative, the denominator is going to have a very big number with a minus in front of it. Then my y values, if I look at the graph, look at what's happening, my y values are going closer and closer to 0. But it cannot be 0, just like x can't be 0. So my y values is also approaching the value of 0. Okay, so again, that's 1 over x, which was approaching 0. The number is so small that we can neglect the fact that it's not 0. That's why we're saying that in this case, it's approaching the value of 0. Okay, so in general then, if I have x, y is equal to n, where n can be any integer number, or any number for that matter actually, then I must remember my x can't be 0, because this n is never 0. It's a number other than 0. So in the product, those two values cannot be 0. Okay, so that's important to remember as looking at, and we call that the behavior of the graph. Okay, so now I'm going to look at what happens. I looked at what happened when x became very big. I'm now going to look at what happens when x becomes very small. To look at that, I have to look at what happens around this point 0. As the x's are zooming in on 0, where are the y values going? And this is a very good opportunity to introduce you to the idea of a one-sided limit. When x, by the one-sided limit I mean, we're working at a specific value of a number, let's say the number 0 in this case that we're going to look at. We're looking at what happens to the right of 0, and we're looking at what happens to the left of that 0. So let's see. When we reduce our values to 0, we are saying that x is approaching 0 from the positive number side. Okay, it's becoming smaller and smaller and smaller, and it's going to 0. So it's to the right of 0. On the left here, I will talk about x approaching 0 from the negative numbers side. That's how I read those little symbols at the top. Now, as x becomes smaller and smaller and smaller and smaller, you can see what's happening to y. Y is really shooting up, and it continues indefinitely. The closer and closer we get to naught, the bigger the y becomes, naught from the positive side. The opposite is true on the other side. The moment we get closer to naught from this negative side, these y values are shooting to very, very small numbers. Remember, if we go down on the y-axis, the numbers are becoming smaller. Okay, so here we are going towards minus infinity, and here we're going towards the positive infinity. So let's write this down. As x approaches 0 from the right-hand side, the y values are approaching infinity. And on the left-hand side of that, as x is approaching naught from the negative side, the y values will be approaching minus infinity. Okay, so that's a pretty intuitive way to look at what the limit represents. We know from school experience that the hyperbole all hyperbole have two asymptotes. We're working with a rectangular hyperbola at school, so you'll be experiencing different hyperbolas, Vitsis, as you go through your calculus course this year. Okay, so what we're doing is we're developing that intuitive. Let's formalize it now with a different example. If I look at the graph that I've prepared for you over here, this will be a representation of y is equal to, and I know you all know this, the asymptote moved one to the right, so this is a representation of that function. Okay, now immediately we've got a denominator with a problem. There's a variable in the denominator, so we have to remind ourselves that the x cannot be 1. That's the problem. Okay, from the function or the rational perspective, let's look at it as a product. If I multiply both sides with x minus 1, then the x minus 1 cancels here, it goes to the other side, so that's now the new product. Instead of having x times y, I've got y times x, I've got y times x minus 1, which needs to be 1. So in this case, x cannot be 1, and our graph shows that beautifully to us. When we draw this and we put it into a computer software program, this is what comes up. There's asymptotic behavior around the number 1, okay? And the y value can still not be naught, meaning that this function will not cross the x-axis, because on my x-axis it actually has an equation, and I think you guys can remember it. The equation of the x-axis is y is equal to naught. It is the horizontal line, y equals 0. And the same for the y-axis. The y-axis has an equation. It is where the x equals 0. So its equation is x equals naught. Okay, so let's have a more formal discussion. Here, x will be approaching 1 from the right-hand side. Another way to write that is that x is dropping towards 1. Some textbooks uses the top notation and other textbooks use the bottom notation. So both of these mean the same thing. On the left of 1, we'll be approaching 1, but from the side of the negative numbers. Okay? And this means x is approaching 1. It's becoming bigger than becoming bigger and bigger and bigger as it approaches 1 from the left. Okay, so what is happening to y? If we are on the right-hand side, we can see y again is going towards positive infinity. From the left, on the left of the asymptotes, the y values just continue indefinitely towards the number negative infinity. It will never ever cross, in this case, cross this vertical asymptote. It can't. Because vertical asymptotes, folks, are indications where denominators in fractions are indeed zero. Okay, so I'm now going to introduce you to the notation that we're going to use to write this idea down. Okay, and that's the idea of a limit. It took 200 years to develop this whole notion, so it's quite exciting if you think about this. I'm going to say there's a limit when x is approaching 1 from the right. Of what? Of the function 1 over x minus 1. The limit for this function when x is approaching 1 from the positive side is a y value. Okay? And that y value, it's talking about what is happening. What is the limit of those y values? Those y values are going to infinity on the right. On the left, the limit when x approaches 1 from the negative side, sorry, this is a bit messy there, of 1 over x minus 1 is saying what is happening to this function when the x's are coming closer to 1 from the negative side. Well, we can see clearly that the y values are going to minus infinity. Now this will become very important in the discussions we're going to have in our next video clip. This idea of them not going to the same value means that there's something that's interfering here. There's a vertical asymptote in this case. The limits around the point 1 are not the same. And we're going to call this function is a discontinuous function. Okay, and what type of discontinuity do we have here? We have infinite discontinuity. And I'm going to write it at DIS to represent the word discontinuity. That means as there's a problem at this value for x, and what is the problem? Well, as I approach the x, the y's are shooting in opposite directions, but they're both shooting to infinity. Okay? So it's infinite discontinuity. There are some textbooks that refer to this as well as under a different name, but at WITS we like to call this an infinite discontinuity. Let's quickly just formulate what happens at infinity. As x here approaches infinity, the same idea is happening. What's happening to y? The y's are going closer to naught. So as x approaches infinity, y will be approaching 0. Okay, now let's see how do we write that in a formal limit notation. We use the word limit, to talk about what this is doing on the function. So if I take the limit when x is approaching a very big number, in other words over here, of this function 1 over x minus 1, that limit will be naught. Now let's just quickly see why that is the case. If you make that number infinitely big, okay, this becomes the limit when x approaches infinity of 1 over x minus 1. Now I'm going to plug in the infinity. So I have 1 over infinity minus 1. Now folks, let's just see. Infinity is so big that if you take 1 away, it's not going to make a difference. This is still going to stay a very, very, very big number. And 1 we saw earlier, as the denominator increases to bigger and bigger and bigger values, the y values increase to naught. And that's exactly what the function is indicating. Now the same on the left-hand side. If we take the limit when x is approaching minus infinity of 1 over x minus 1, we see the same thing happening. Those values are going towards 0, even if it is a very, very large number without the negative, the moment we put a negative in front of it, it's a very small number that's negative. Okay, and that is moving towards 0 as well. So our limit, the same way as what happened here, is indeed 0. Now in this case, it's important to notice the following. For the limit here at minus infinity is going to naught. The limit at positive infinity is also going to naught. And remember, that limit is a y value. So that tells us two things, that there is a horizontal asymptote at the value y equals naught. Okay, and there can only be a horizontal asymptote if those y values were approaching the same values as x was approaching positive infinity and negative infinity. That means this limit exists because it's going to the same value. Okay, it's absolutely, both of them are going to 0, where for the limit when we were approaching 1, they were going to positive and negative infinity, which meant there's definitely an infinite discontinuity. As I said, other textbooks calls it a jump discontinuity, but we prefer the word infinite discontinuity because it's going to infinity. Here we have a horizontal asymptote. When x becomes larger or very, very small, they approach the same value. That means that limit exists, which means there's a horizontal asymptote where y is naught, in other words, the x-axis. Here, there was a vertical asymptote where x became closer and closer to 1. Okay, I think that's what's most probably what you can deal with now. So I want you to go, you have to go to your textbook and go and do some reading on this topic and see what the textbook says to you about the idea of a limit, so that when you watch the next video we're going to shoot for you, then you understand exactly what we're talking about. Thanks for watching.